Hey, it's Tim the Tutor here with Free Test Prep Online, and in this video we're going to review Alkane Nomenclature. Organic molecules are named according to IUPAC rules, and in general, molecules are named in the following manner. You have your substituents, plus the parent, plus the function group. Now the parent is the longest unbranched or continuous carbon chain that contains its primary functional group. And the name of the parent is based off the prefixes shown in this table. The most important ones for a student to remember are when the carbon chain is 1, 2, 3, or 4. And those prefixes are going to be meth, eth, prop, and bute, because those are unique to chemistry, whereas once you get to 5 or more in the chain, then we just use normal mathematical prefixes such as pent for 5, hex for 6, etc. The functional group is going to be a unique arrangement of atoms in a molecule that gives the molecule its unique characteristics. There are many functional groups in organic chemistry, but this video, of course, is going to focus on alkanes, and those simply end with ANE. Last, we have the substituent, which of course shows up first in the name, and substituents are not a part of the parent chain, rather they branch off of it. There are also many types of substituents, but again, this video is going to focus on the alkyl substituents, or the chains of carbons and hydrogens, and all these end with the YL suffix. Let's start off by naming unbranched alkanes. An alkane is unbranched or continuous if you can start counting carbons from one end to another end without it branching into two directions at any point. So you can see in this image that I have everything from methane, which is just CH4, all the way to dodecane, which is a continuous 12-carbon branch. You can see that all we need to do is use the prefix meth, eth, prop, or bute for 1 through 4, and then pent through dodec for 5 through 12 to name these alkanes. For alkanes, it doesn't matter how bonds are rotated in space because single bonds can rotate freely. It only matters if they're continuous. So both of the examples at the bottom of this page, for example, are octane. Now let's move on to talking about alkyl substituents, both simple unbranched ones as well as some common ones. Unbranched substituents are named just like parent alkanes, except the ANE is replaced by the YL suffix. Sometimes an N is placed before the name, so for example, instead of propyl, it might be called N-propyl, to indicate that it is a normal or unbranched alkyl substituent. So you can see the 4 on the left, methyl, ethyl, propyl, and butyl, as simply straight chains of 1, 2, 3, and 4 carbons. Most organic chemistry courses will also want you to know the common names for these 4 propyl and butyl derived substituents on the left. So we can see isopropyl has 3 carbons, but rather than connected all in a row, we're connected at that middle carbon. Then we have isobutyl, secbutyl, and tertbutyl. You can see all of those have 4 carbons in their chain. For secbutyl, if you ignore the parent chain, notice that the substituent is connected at a secondary carbon, hence sec. Likewise, for tertbutyl, once again, if we ignore the parent chain, the substituent is connected at a tertiary carbon, hence tert. Now, to completely name a substituent, it must include the number of the carbon of the parent chain to which it is attached. The format is to include the number, followed by a hyphen, followed by the alkyl group name. So there we have propane, and I've numbered 1, 2, and 3 for the carbons, and we can see coming off the 2, there is a methyl group. So we call that substituent 2-methyl. So let's name an entire alkane with one alkyl substituent. So the way we do this is first we name the parent chain by finding the longest unbranched carbon chain. What we're going to do after that is we're going to number the longest chain, giving the lowest possible number to the substituent. Next, we'll name the substituent, and then finally, we're going to put it all together, leaving no spaces between the substituent and parent. So let's do an example. I have the same alkane drawn 3 times here, and I've numbered it in 3 different ways. Go ahead and pause the video and follow the instructions at the top of this slide to see if you can figure out what the name of this molecule is and which of these numbering systems is correct and which ones are incorrect. You can see here that actually the first two methods of numbering are identical to each other because they give the same overall name of 2-methyloctane. So they're both correct ways of numbering. The third way of numbering, which would give 7-methyloctane, is incorrect because, again, we want to number the chain giving the lowest possible number to the substituent. So if we can choose between 2-methyl and 7-methyl, 2-methyl is going to win. So this last one, of course, is incorrect. For the next example, I once again have a molecule that is numbered in 3 different ways. Go ahead and pause the video again and try to determine which of these is correct and which of these are incorrect. You can see here that the first 2 structures are incorrect. The first one is incorrect because it doesn't properly identify the longest carbon chain. It only puts it at 7, which is a heptane. In the other 2, we can clearly see that we have an 8-carbon chain, an octane. The second one is incorrect because it numbers it from left to right, which puts the first substituent at the 6, whereas in the final structure, you can see that it puts the substituent at the 3. So the final structure follows all of the rules for naming. So 2-ethylheptane and 6-methyloctane are incorrect, and the correct way to name this structure is 3-methyloctane. When it comes to naming alkanes with 2 alkyl substituents, things get a little more complicated. Once again, we're going to name the parent chain first by finding the longest unbranched carbon chain. When it comes to numbering the longest chain, however, we're going to give the lowest possible number to the first substituent. And in the case of a tie, we're going to give the lower number to the substituent that comes first alphabetically. After that, we're going to name each substituent and then combine like substituents. For example, if there were a 2-ethyl and a 3-ethyl, we would combine them to a 2,3-diethyl. In the table in the bottom left, you can see I have combinatory prefixes shown for the number of like substituents that you have. So again, if you have 2 like substituents, we use di. If we have 3, tri, and so on and so forth. Once we've done this, we put it all together alphabetically, putting hyphens between individual substituents, commas between subsequent numbers, and leaving no spaces between the final substituent and parent. Now, as a note, when considering alphabetical order, prefixes do not count, with the exception of the iso prefix. So as an example, butyl, isobutyl, isopropyl, dimethyl, and propyl are in order alphabetically according to that rule, where the B comes before the I in isobutyl and isopropyl, and we don't count the D in the prefix di, so we count dimethyl as an M, and then we have P for propyl. Let's name the structure on the top left by following these rules. So first we're going to find the longest unbranched carbon chain, and that looks like it's going to be 8. Now we're going to number the chain, giving the lowest possible number to the first substituent. So it looks like if we number it left to right, we're going to get the first substituent at the 3 position. But if we number it right to left, we're going to get the first substituent at the 2 position. So that's how we're going to number it. Now when we name each substituent, we can see that we have a 2-methyl and a 6-ethyl. Now we're going to put it all together alphabetically, noting that E comes before M. So the final name for this is going to be 6-ethyl 2-methyloctane. For the structure in the top right, it looks like the parent chain, once again, is 8, so we have another octane. However, when we number this from left to right or from right to left, it looks like we're going to get a 3 as the first substituent either way, so we have to go to our tiebreaker case. For 2 substituents, the tiebreaker is alphabetical. So we have an ethyl group and a methyl group. So E comes before M, so we're actually going to number our chain from left to right. Now we can put the numerical prefix before each of these substituents, so we have a 3-ethyl and a 6-methyl. When we put this all together, that is going to give us 3-ethyl 6-methyloctane. For our last example here, I want you to pause the video, try to name this one yourself, and then come back and check if you were correct. if you got 2,7-dimethylnonane, then you're correct. The most common mistake here is not finding the longest carbon chain, which of course is 9. A lot of students will stop at 8 and then say that there's an ethyl group and a methyl group. But if you actually count the longest chain, it is 9. So of course we number from right to left because that puts our first substituent at a 2, where if we numbered from that top left to the right, then that's going to give us a 3 for the first substituent. Of course, we need to combine the 2-methyl and the 7-methyl, giving us that 2,7-dimethylnonane. When it comes to naming alkanes with 3 or more alkyl substituents, once again, we're going to start with the parent chain. Once we find the longest chain, now we have to number it. Once again, we're going to give the lowest possible number to the first substituent. But now we might have 2 different tiebreaker scenarios. For the first tiebreaker, we're going to give the second substituent the lowest possible number. Now, if the second substituent from both directions is also the same, we go to the third, then the fourth, etc. For the second tiebreaker, we only use this if we cannot break the tie via the first tiebreaker. And in this case, we give the lower number to the substituent that comes first alphabetically. Then, just like before, we're going to name each substituent, combine any like substituents, and then we're going to put it all together alphabetically. Let's look at the first example on the bottom left. The longest carbon chain is 10, and if we number it from left to right, that puts our first substituent at carbon number 2. From right to left, we also put it at carbon number 2. So we have to go to our first tiebreaker, which is to give the second substituent the lowest possible number. So from left to right, we get a 4 for the second substituent, but from right to left, we get it at the 7. So we've broken the first tiebreaker, and we're going to number this chain from left to right. When we name the substituents, we have a 2 and a 9-methyl, so we're going to combine those to 2,9-dimethyl, and we also have an ethyl group at the 4. So when we put this all together alphabetically, that's going to give us 4-ethyl, 2,9-dimethyl decane. Now that we've named an alkane with 3 substituents together, go ahead and do the one on the right by yourself. So pause the video and come back as soon as you're done and see if you're right. Hopefully you counted that the longest chain was 11, not 10. That gives us an undecane. Now there's 2 ways to number this. So I've numbered the chain in blue one way and then in red another way. And you can see that we have substituents at the 4, the 6, and at the 8 in both directions. So we can't use the tiebreaker because it's 4, 6, 8 either way. So we have to go to the second tiebreaker, which is alphabetical. So among ethyl, isopropyl, and methyl, E comes first. So we're going to use those red numbers to number this chain from right to left. When we put everything together alphabetically, that's going to give us 4 ethyl, 8 isopropyl, 6 methyl, undecane. Now let's talk about naming cycloalkanes. Cycloalkanes are simply alkanes that have rings. And we name cyclic alkanes just like unbranched alkanes, except we add the prefix cyclo to the front. So for example, if we have a ring made up of 3 carbons, we call it cyclopropane. So you can see here cyclopropane, cyclobutane, cyclopentane, and cyclohexane. Oftentimes, cycloalkanes have branches off them that are acyclic alkanes. In these cases, we have to determine which chain, the cyclic or the acyclic one, is the parent chain. The cycloalkane is the parent chain if it is the same length or longer than the longest unbranched acyclic chain. So on the right, we have ethyl cyclohexane. So the cyclohexane has 6 carbons in it, and the ethyl group has 2. So the cyclic component is the parent chain. To the right of that, we have butyl cyclobutane. Here, the ring is a 4-membered ring, and the acyclic chain is also 4 carbons long. Because it's a tie, preference goes to the cyclic structure. So the substituent is butyl, and the parent is cyclobutane, hence butyl cyclobutane. I want to point out that if a cycloalkane has only one substituent, a number need not be assigned to the substituent, as it is understood to be at the 1 position. Now, if the longest unbranched acyclic chain is longer than the cyclic component, the acyclic component is the parent chain, and the cycloalkane is the substituent. On the far left, we have 3-cyclopentylhexane. The cyclopentane has only 5 carbons, whereas the acyclic chain has 6. Hence, the hexane is the parent, and cyclopentyl, note we drop the ANE and we put a YL since it's a substituent, shows up at the 3 position on the parent chain. To the right of that, we have 1-cyclopropyl butane. Once again, the cyclopropyl is the substituent, it's a 3-membered ring, and the butane is the parent. And we have to put where it's located, and it's located at the 1 carbon on the butane. Other than that, all the regular naming conventions discussed previously still apply to cycloalkanes. So take note of the 2 cycloalkanes on the right. Go ahead and pause the video and confirm that those names are what you get when you try to name those 2 molecules. Last, I want to go over how to name complex alkyl substituents. Now, oftentimes in organic chemistry courses in college, you aren't required to know how to name complex alkyl substituents. However, some courses may make you do this, so I wanted to review this. If this doesn't apply to you, don't worry about watching this part. So for a complex substituent that doesn't have a common name, or if you want to use a systematic name for a complex substituent instead of a common name, what you do is you find and number the longest unbranched carbon chain, starting by numbering the carbon directly bonded to the parent chain with a 1. Then you're going to name the groups coming off the parent substituent, like you would as if they were substituents off a regular parent molecule. Then you're going to end the entire substituent with a YL, like you normally would, and put the entire substituent in parentheses. Let's look at this isopropyl group. Isopropyl is the common name, however there is a systematic name for this complex substituent as well. So we're going to follow these directions. Coming off the parent chain, we're going to number the longest chain with a 1 and a 2. So this is an ethyl group, but coming off the ethyl at that 1 position is a methyl. So how do we name this? We say, in parentheses, 1-methyl ethyl. We can do the same thing for the other 3 common groups that we know. So for isobutyl, we have 1, 2, 3, and coming off the 2 is a methyl group. So we have 2-methylpropyl. For sec-butyl, the longest chain is 1, 2, 3, and we have a methyl coming off the 1, so we call this 1-methylpropyl. And last, for tert-butyl, the longest chain is just 2. And we have 2 methyls coming off the 1 position, so we call this 1,1-dimethylethyl. Now go ahead and pause the video and try to name this complex alkyl substituent. Here we have a long chain of 4 coming off the parent chain. So that is a butyl group. Coming off the 1, we have a methyl, and coming off the 2, we have an ethyl. So to name this group in its entirety, again we go in alphabetical order, we have 2-ethyl, 1-methylbutyl, and the entire thing is in parentheses. One thing to note about complex alkyl substituents is that their prefixes actually count alphabetically. For a complex substituent, the first letter in parentheses will always count towards any naming rules and tiebreakers involving alphabetical order. So we have a substituent, 2,3-dimethylbutyl, and another substituent, ethyl, on this cyclohexane. Normally, we wouldn't count the D in dimethylbutyl because it's a prefix. However, because it's a complex substituent and it's found within parentheses, we do count the D. So, dimethylbutyl comes before ethyl, and hence we have this name overall. At the 1 on the cyclohexane, we have the 2,3-dimethylbutyl, and at the 3, we have the ethyl. So we have 1, 2,3-dimethylbutyl, 3 ethyl cyclohexane. And of course, just as a reminder, for regular substituents that are not found in parentheses, iso is the only prefix that matters for naming rules and tiebreakers involving alphabetical order. So for the cyclohexane down here, we have 3-ethyl 1,1-dimethyl cyclohexane, and you can see that the E comes before the M because we don't count the prefix di in this example. If you got something out of this lecture, please feel free to like this video and subscribe to this channel. If you have any questions or comments, leave a message below. And last but not least, if you want more help or want easy access to valuable organic chemistry resources for free, be sure to check out the notes underneath this video with a link to join our community.